For years, to make a computer read a sentence, you fed it words exactly like items on an assembly line, one by one. This step-by-step method was called a recurrent neural network. For years, it was the standard way to teach machines how to process human language. But the assembly line had a serious flaw. The system had a short memory. If you fed it a long paragraph, by the time it reached the final word, it had often lost track of the context from the very first word it read. It also had a strict speed limit. Because the machine processed things sequentially, it was unable to look at the fourth word until it had completely finished analyzing the third. You couldn't even throw more computer chips at the problem to speed it up. The math required the system to wait in line, regardless of how powerful the hardware was. This sequential bottleneck meant that early models hit a ceiling. They struggled to grasp complex context, and training them took huge amounts of time. In 2017, a team of researchers at Google proposed scrapping the assembly line entirely. This diagram illustrates their new architecture, the transformer. It's split into two main sections, the encoder on the left, which acts like the ears to process the incoming sentence, and the decoder on the right, which acts like the voice to build the translated response. The engine driving this structure is a concept called self-attention. Instead of reading words in a row, imagine a detective's crime board where every word in a sentence is pinned up all at once. With the whole sentence laid out simultaneously, the machine can instantly draw strings between the pins, calculating how strongly every word relates to every other word. By looking at the full picture, the computer maps out the complete web of context. It treats every sentence as an interconnected landscape of meaning. To see why this matters, look at a translation problem the researchers used in their paper. The law will never be perfect, but its application should be just. If an old assembly line model tries to translate the word it gets confused. It needs to know if its refers to the word law to get the grammar right. But those two words are separated by too much space for the old system to reliably connect them. Self-attention solves this problem instantly. On the crime board, the system snaps a direct line right between its and law. Physical distance in the sentence no longer matters. The connection is weighted entirely by how much the two words depend on one another for context. This ability to resolve ambiguous phrasing across long gaps meant the machine was grasping actual meaning. It was finding the internal logic of human speech. The transformer goes even deeper. It doesn't just look at the board once, it uses a mechanism called multi-head attention. Think of it like assigning 8 separate detectives to study the exact same crime board at the exact same time. Each head focuses on a different type of relationship. One tracks the grammar, another follows the subject, and a third watches for the emotional tone. Because these processes run side by side, they build a deeply multi-layered understanding of what is being said. Dividing the task among these parallel heads allows the AI to capture the extreme nuance of language without slowing down the system. When the researchers tested this architecture, it broke previous records for translation quality on both English to German and English to French benchmarks. It achieved those results while training with incredible speed. Because the system processes the whole sentence at once, the work is handled in parallel. What used to take months on supercomputers took this model just 3.5 days on a few standard graphics cards. This chart shows another benefit. We can see how the machine thinks by tracing the literal strings it draws between words. Here, different colored heads link the word making to the phrase more difficult, despite being separated by 5 words. The architecture was so flexible it successfully handled entirely different tasks, like mapping sentence structures, even with very little training data. By giving machines the ability to map connections across an entire context simultaneously, attention is all you need produced a top-tier translator and established the foundational architecture for the entire modern era of artificial intelligence.